Fantastic. So first off, it's really great to have you all here today. I really appreciate it. I got to do a workshop with you all last year, and it was a lot of fun. So I appreciate getting to do it again. And so last year I gave a talk on for the IMSI Summer Institute on optimal control methods and optimal control modeling, which I enjoyed giving, and it's still online if you want to check it out. But one of the things that we kind of took for granted when I did that workshop was that you all know how to simulate the movement of an organism, an animal, a robot in my case. So we decided to sort of back it off a little bit this year and have our topic be about how you simulate movement from scratch. Because I don't know about you all, but I'm not sure when in your education you learn how to write computer simulations of movement. I mean, if you're, I'm an engineer. By the way, hello. Let me start over here. Hello, I'm Christian Hubicki. I'm an associate professor of mechanical engineering. I am. It doesn't say biology in my title, but I love collaborating on biology projects. And as we all know, there are many ways that biology applies to many different disciplines and movement science. Um, so I'm going to talk today about how you simulate movement, because simulation is something you do a lot in my field. So, many of us know all about, have seen a lot of Monica's work. Make sure we get this going here. All right. So here's an example of a thing that moves. Monica's, I don't know if it's your original research subject, but probably one of your most famous is the guinea fowl. We've seen many videos of these things running around on obstacle courses very stably, and they move, right? And experiments are so important for getting data out of animals. And I was actually put on a project working on this with Monica back when I was a grad student. But my field is less about animals directly and more about my subject, robots. I work in robotics. Okay, so where do we connect on this? And a lot of it is in the field of simulation. How do we make a simulation of an animal? Okay, in a way that's helpful. And why would you want to do that? Okay, and in robotics, the reason we want to have simulations is we want to be able to write controllers. And so one thing we will do is we will take a robot, we will write a computer simulation, and have an algorithm try to optimize how that simulation moves to come up with a controller for a walking robot. And that's what this here is. So the first thing we had to do before we control this robot was how to simulate it. Okay. And so that's my specialty, and particularly the optimal control thereof. But more importantly, for I believe the Summer Institute, is that simulations are math models, right? It offers another way to look into and interrogate the motion of organisms. If you have a simulation, you can try all kinds of things you would never think of trying with an animal, and test all kinds of hypotheses as to why the animal is doing what it's doing without an experiment, or more importantly, in complement with an experiment. Probably very, right in this paper that Monica had written back in 2006, she used a pretty simplified math model right here of what's called a spring-loaded inverted pendulum to model how this guinea fowl steps into an obstacle and then falls forward, but and yet still maintains its stability. Okay, so simplified, and to do that, Monica had to write a computer simulation of movement, right? And from my standpoint, from a robotics standpoint, math models are also important for how you design robots as well as control them. That if you have some simple bio-inspired model for simulation, something simplified, you can use it to inform how your robots are built as well as how to control them. And theoretically, if you have a reasonable bio-inspired model that guides your control and your design, you can end up with animal-like movement as a consequence. At least that's a hypothesis we've seen that we've toyed with a lot in the past. And math models can come in all shapes and sizes, right? This is OpenSim. It's been downloaded hundreds of thousands of times, which allows your models to be complex and musculoskeletal. And probably is what a lot of people might think of when they're thinking of simulation, is these really complicated models. But they can also be incredibly simple. This is a very simple model of a predator-prey interaction modeled by my student Jacob Hackett. The idea is that this little rat is running away from some kind of owl that's chasing it down. And you have a very simplified model, which is just a little mass that's being pushed around by a force, and they're trying to avoid each other using optimal control, right? So You can also use optimal control. You can also use models with optimal control for prediction. Okay, that if you have a reduced order model, a very simple simulation model, and you hypothesize what the animal might want, what its objectives are, what its rewards are, right? And you take that model and you give it to an algorithm that optimizes its motion with control, okay? You can have it make a prediction as to how the animal will move. What we're looking at right here is a sagittal plane trajectory of a stance phase and a flight phase for a running guinea fowl, or at least a simulated running guinea fowl. And there's your ground reaction forces right there that you would typically see if you measured them in the ground. We can try to make predictions as to how they would move on different terrain. Okay, and this is an example from a paper that Monica and I had written together with one of her intrepid graduate students. It was a real humdinger of a paper, lots of stuff involved. But one small piece of it was making an optimal control prediction of how the ground reaction forces can reflect the energy injection of a stance phase across all these different species of birds. Okay, so what I want to impart upon you today are some of the basics of how you would simulate these animals, all right? And it can become very complicated. Like if we go back to our to the OpenSim model, you know, for if you're trying to work with a very complex musculoskeletal model, thankfully they already have packages you can download and some tutorials that you can run. But one thing we find, at least I found in, of course, throughout my time as a researcher, is having a bespoke, simplified model can be super helpful in a lot of ways for being able to interrogate how an animal would move and test hypotheses about it. So that's what we're going to do today is figure out how to take a much simpler model and then actually write a computer simulation. We're going to do it in MATLAB today from scratch, in case you have never done this before. And I'll cover some of the basics of how we're going to do this. And so what we're going to do today is we're going to try to simulate some hopping with a spring-loaded inverted pendulum. Okay, it's a classic model, all right? And so we're going to start from scratch. We're going to make a mass with a spring, maybe a little damper, and have it hop around. This one has a second leg in it just because why not? But we can see how far we get today. And as a result, we're going to cover how we're going to do simulation at all, okay? All the basics of it. We're going to get the equations for this model, and we're going to simulate them. And we're going to see how it goes. So with that, I'd recommend opening up MATLAB. You don't have to download any code to start. You don't need any toolboxes. Just open up MATLAB and we'll get started. And I'll start drawing out things on my little whiteboard here to get us started. So if you want to simulate movement, okay, so simulating movement. Okay. The first thing you're going to need is a model, or what we call in our business a dynamical system. Okay. And what that means is we have some equation that defines how it moves, how the system moves, given its current position and state and any control that you want to add. Okay, and that sounds pretty abstract, and I'm going to start talking about a little bit of math. But just to be clear, the kind of math that we're talking about for this talk is, do you know what a derivative is from calculus? Right? That's my starting point for how we're talking about math today. I'm sure many of you are experts in simulation, at which point, you know, treat this as a nice vacation of thinking about simple simulations here. But for those who haven't, and I imagine that's a lot of people, that's all you need to know. What is a derivative? Okay, so. And that's important because we define dynamical systems which are systems that vary with time, which is a lot of things like movement, appropriately enough, okay? By the time derivative of key variables. And those key variables, they have a special name. They're going to be called state variables, and we'll get to that in a second, right? Basically, you're getting a crash course in the basics of dynamical systems and how you simulate them, okay? Or what's a survival guide. How about that? All right. So now recall we have so imagine, and you take a typical population model. Example, a population model. Okay. Let's say you have a population model for some population P of rodents in the desert, right? And how much do they multiply, right? So you can see that it's varying with respect to T, which is time. Okay? And so our dynamical system would be defined by how much the population changes, dp dt, your time derivative, is going to be dependent upon your population. It's going to be dependent upon your population times some alpha constant right there. Okay. Rodents in the desert, no better system. I agree, Clint. I agree. Okay. Fantastic, right? So basically, the more rodents you have, the more they're going to multiply. Now, of course, you're going to be limited by environment, so you can add other terms here, but this is a really simple population model, right? So basically, you're saying, this is how much your population changes. Okay? It's a derivative, right? It's derivative with respect to time, right? And when you have an equation with derivatives in it, does anyone know what that's called in math? Anybody? I know many of you are being polite and not answering because you're waiting for the students to answer. But yeah.
Differential equation?
Differential equation, Casey, that's right. It's called a differential equation, right? Hope this isn't overly tutorial for everyone. Hopefully someone is learning something. It's a differential equation, right? It's that thing that if you're not a math major or an engineer or something like that, you might not have to take necessarily as part of your curriculum. But that's all the differential equation is an equation with a derivative in it, right? And solving differential equations by hand sometimes can be easy. This one we can solve by hand. Sometimes can be hard, right? So basically, if we manage to solve this differential equation, it will tell us what the population of the rodents are going to be in the desert for all time. For all time, right? Awesome, great. This one we can solve just by, if you took a differential equations class, it's just going to be an exponential is what it's going to turn out to be. You need an initial condition, et cetera, et cetera, et cetera. In fact, yeah, so anyway, this is your population model, right? But there are some systems there are some equations that are harder to solve by hand, right? In fact, I'll write out the answer here just for everyone's completion's sake. Oh, the solution would be P of T is equal to some constant C times E to the alpha T, right? That's the solution. So we would know it has this exponential curve, and this little constant C right here, that defines the initial condition. That's your starting population, for instance, right? But guess what? You don't have to know how to do that for today. You don't need to know how to solve these by hand, right? And there's a good reason for that, is because while this is a simple system, I'll give you another simple system. I will swing it. Here's the pendulum. We all know pendulums. We've probably seen them all the time under gravity. I can write out the equations of motion for a pendulum. All right, sorry. So I can write we can write our equations for our differential equation for a pendulum. Okay, under gravity. So I'm going to draw a pendulum. There you go. Not my best work. got a little mass at the end. You got some length L for your pendulum. You're under gravity. Okay, pendulum, and this is some angle theta of t that can change over time. That's how you have your dynamical system. It changes over time, right? So you could write out the equations from this by just doing a force moment balance using a free body diagram. It would save us a little bit of time today, and say that the second derivative of theta of t dt is equal to minus g over L sine of theta of t. This would not take too long to derive. In fact, we'll have to derive some equations for our spring-loaded inverted pendulum, but I'll save us some time. Here's a differential equation. That doesn't look too bad, right? Does anyone know how to solve that by hand, like I did the population model? The answer should be no one, because it's impossible. It is literally an impossible equation to solve with elementary functions, sines and cosines, exponentials. We know this fact. We've known this for a very, very long time, right? So it's all lost. So does that mean we hang up our hats? No. Clearly, we know how to simulate a pendulum. You know, we have had physics simulators for a long time. We have video games with dynamical systems like pendulums. We have robots, which are basically a bunch of joints that are connected together. They're pendulums. So what do? So we solve differential equations approximately. Okay? That solution for that population growth model, that's an exact solution. That is literally the answer to the math question, right? If we can't get that, we can at least get close, all right? So the way that so this is often called, solving numerically. And you are all, if you're doing any kind of simulation in any field, any domain, if you're playing Zelda and you're lobbing bombs at creatures, if you're simulating an animal in OpenSim or something like that, they are approximately solving differential equations. That's all simulation is. Let's put this in red. Simulation of dynamical systems is just solving differential equations. That's it. Okay, that's it. Okay, so anytime you see a simulation, that's what they're doing of a dynamical system, right? So what do we do? Okay, so how? All right, and we'll cover one of the simplest ways, which is to take the definition of a derivative. Let's take a definition of a derivative. Some variable x of t dt, right? And what is that? Okay, well, if you remember calculus, the derivative is limit as some small delta x goes to 0. Sorry, delta t. I apologize. Delta t, okay, of the quantity x of t plus delta t minus x of t all over delta t. I jumped straight to the math. I shouldn't have done that, right? What I should do is I should say, hey, let's say I have some graph of time and this variable over time, right? And whoa, there it is. That's what the graph looks like, right? If I want to know what the derivative is at that point, in effect, what you need is the tangent at that point, and then you want to know what the slope is, right? And the way that you get that is by saying, hey, I'm at this time t here. Now I'm over at some tiny, tiny different spot over here, t plus delta t. I say, hey, what's the slope between those 2 points? That's what a derivative is. So what is a derivative? And the formal definition is when t, delta t here, goes to 0 in the limit. That's what we learned in calculus, right? But what if it wasn't literally going to 0, but instead was super small, okay? What if delta t is really small? Okay? Then we would say the same equation over again, where we would say, okay, well, dx dt of t is approximately equal to x of t plus delta t minus x of t all over delta t. So instead of the limit as it going to 0, you just say, hey, just, delta t is small. It's small, and this is almost right? Which is cool, because what that means is I can then say, hey, in the future, I want to know what I want to know what x is in the future. That's what solving a differential equation is. I want to know what's happening in the future, right? I can just solve for this using good old algebra. Multiply both sides by delta t, then add x of t to the other side. I can just solve that really quick. And I would say, well, x of t plus delta t is approximately equal to x of t plus dx of t dt times delta. Sorry, iPad's misbehaving. Times delta t. All right? Hopefully people can follow that algebra well enough. We just put this on the other side, and then added this to the other side, then rearranged them back and forth. That's it, right? So now we know approximately what the future will look like based upon where we are now at the current time t, plus the rate of change, the time derivative, times delta t, right? This is a super common method. It's called Euler's method. Okay. And it's near and dear to my heart because, one, it's super easy. We just derived it. It's done. Also, my postdoc advisors was Leonard Euler. So probably like a lot of people in this collaboration, to be honest, but got to do well by great grandpa. Okay. Anyway, this is the simplest way. This little equation here is the simplest way that we can approximately solve a differential equation. And what does it mean? It means that we have some tiny time step t, and we say, hey, where do we start? We add this term. We say, hey, how much are we changing? Multiply it by how long we're changing for, and then we get the next time step. And then we repeat over and over and over and over and over and over again until we simulate it for so many little time steps that they add up to a long period of time. So let's go back to our population example. Where we said we had some dp of t dt, some change in population over time is equal to some constant alpha times whatever your population is. And we say, here's time, here's our population, here's time 0. And we have to tell ourselves, what is the starting population? And more generally, we call it the initial condition. Because that matters, right? Now, I'm no ratologist, but I imagine when there are 0 rats, they proliferate at a different rate when there are 2 rats, right? To start with. That's just my lay understanding of the matter. Okay? So let's say we start off with some number of rats. Then we know, confirmed. Okay, Clint confirms this scientific fact. Thank you, Clint. Good. All right. So we are currently at this time here, right? This is now. Welcome to now. All right. And the amount of time, so now we're going to use Euler's method. And by the way, the cool kids call it Euler's method. My granddaddy would like it that way, not Euler's. Okay. I asked him. Okay. All right. We're going to say, hey, the next time of P plus some delta T is going to equal the sum P of T, the current population, plus the change in population, at the rate of change of population, times this tiny delta T, right? So let's find out, after one small time step, what our population is going to be. Well, we know what our population is now. We said it's that, all right? And now we say, okay, well, what's the change over time? Well, we have this equation up here. It's this alpha P of T, right? Let's assume alpha is positive. This is a positive rate of growth. These are proliferating rats, okay? That means that this is going to be some positive number proportional to the current population. And you multiply it by some delta T. So this is all going to be some positive number, right? So after some tiny period of time, delta T, that means it's going to go whoop, like that, up a little bit, right? Now we're going to step, now this is now, right? That's now. Okay, and now we're going to move forward again in time because we want to know what happens over time. And now our population is bigger. It's bigger there than it was here. So when we're doing this calculation again, we're moving forward in time again. We now take our current population, which is this, and now we add this term, which is now more because our population is now bigger, right? So it goes up at a greater rate of change, right? And guess what? It keeps doing this, right? And that's going to approximate, that's going to end up looking like the answer that we all know from people who took differential equations or know how to solve them. It's going to look like e to the AT. It looks like that. That's an exponential growth, right? Multiplying like rabbits or rats in this case, right? That's what it looks like. So we didn't have to know all the cool tricks from the differential equations class, how to solve that equation. It's okay. We got this approximated version of it, right? It just takes a lot more sort of churning of the numbers, right? We have to do this equation over and over and over again, right? Okay. So that's it. In fact, why don't we code up the multiplying? You know what? This will be quick. Let's code up in MATLAB the rat population model. And we'll show you how simple it can be. All right. So I want to go back over to ye olde MATLAB. Actually, I want to go back here. Oops. I'm raising my. All right, and there we go. So let's make I have MATLAB open here, and I just got a very simple script open. I just opened up a new file. All right. We're going to create a new file. We're going to call it population sim.m. Can you read that? I can make the text bigger if it would be helpful to read it. How about now?
A little bigger might help, yeah.
Okay, let's do that. All right. I'm also recording this in 4K on my own computer, Victoria, if we want to upload that instead. So
that'll be great.
All right,
thanks.
so you got it. So, but hopefully people read it now. So I'm going to save this file. I'm going to call it population sim.m. Okay. All right. Written by myself and friends. That's what the original et al. Latin stands for. Okay. All right. We're writing this together. All right. So today, it's the 21st of August of the Common Era, so there's no confusion. All right. So we're just going to simulate the population growth of rats without resource limitations. Right? Nothing is, or predation, I guess. Anyway, simple model, right? So for those it's been a while to do MATLAB, to do any MATLABing here, first thing I like to do when I create a new MATLAB script is I clear everything. Okay? And I clear everything. The way I do is I say CLC. All it does is clear the screen. It clears the main screen if there's anything down there. Clears all the variables. And closes all the plots. All right? And clear everything. Okay? All right. So now I need to define my simulation parameters. Let me actually pull up the math again. So what are we going to need to know? Oh, actually, let's put this over here. Boom, boom, boom. So what are we going to need to know? We need to define what our delta t is. We have to define what our alpha is. And we have to define our population at time 0. That's our initial pop, right? Okay. And we also want to know what the final time is. How long do we want to simulate this for? How long do we want to simulate this for? Those are the 4 things that we're going to need to define. Okay. So let's define those parameters here. Actually, let me move this aside so we can see it in spite of everything here. So we got, so define our parameters. Okay. All right. So we're going to get call it our delta t. Make it 0.01. Okay. All right. It needs to be small. Now, how small? Good question. So glad we didn't use clear hall, bad habits still lingering from your student days. Oh, thanks, Jordan. That's good to know. Yeah, I just use clear these days. All right. So dt. Let's get our T final. Let's simulate for 10 units of time. Now, I was a bad boy. I did not define my units in this model, but we're going to move. We're going to press forward to get this out the door so we can keep moving forward. So this is going to be our final time. All right. We're going to need our alpha, which is some parameter. I'm just going to call it 0.5. This is some rate of population growth. Okay. And we've got our initial population. We'll call it P0. We'll start with 2 animals. All right. Initial population. Okay. Okay. So what we're going to do is, in order to do this simulation where we're constantly, reapplying Euler's method over and over again, what are we going to need in the encoding structures? We're going to need a loop, right? So what we're going to need is a simulation loop. Okay. I'm going to go a little non-linearly in terms of the code and motivate some things later. But what we're going to want to do is start at our first time, which is time 0, compute what the next population is, and then the next, and the next, and the next, and the next. And we want to store it all in a big vector or in a big array. Okay. In MATLAB, we call arrays vectors for the most part. And it's just good practice to say, hey, let's define all of the size of all of our vectors beforehand and not just make them bigger as the loop goes along. And this is called pre-allocation. Okay. It helps speed up your simulation and it's better for memory usage. It's just good practice to do it. Pre-allocation of arrays. So what we're going to need is we're going to store our time array in an array. And the way that we can store it is we can say we want it to start at time 0, go in increments of dt, and end at t final. That's the MATLAB syntax for it with colons, and that will count up, right? All right. And they're going to create a population array. Now, we do not know what the population is going to be at all these different time points, but so for now, we'll just call them 0 and change them later. So in MATLAB, we would say, hey, zeros, and we want it to be the same size as the time array, because for every point in time, we want a population. The way you can say this is say, hey, what's the size of our time array? And it'll create zeros of the exact same size. That's it, right? What I can do is I can run the code to make sure I don't have any errors. No errors yet. Okay. All right, so now we have our time array, population array. Then we need to set our initial condition. Okay, which means that the first element of our population array, I'm using tab to help complete in case you're not familiar with the syntax. So the very first element, and in MATLAB we would say open parentheses 1, close parentheses. The very first element, the very first number in that list, let's change it to our starting population, which is P0. Okay, cool. Now we need to do a simulation loop. Now, if you're doing a loop with a known number of steps in the loop, we use what's called a for loop. I'm sure many of you are super familiar. So you say for, and you have some iteration variable. I call it iter. In MATLAB, I don't like to call it I because I is already taken as the imaginary number. I don't use M because M is almost always mass in my simulations, and I have made my mass increase over time by mistake in my simulations by calling it M. Yes, yeah, I'm glad you appreciate Victoria. So all right. So and you're going to go through 1 colon the number of elements. It's NUMEL. That's the number of elements in your time vector, in your time array. So time array. Okay. And one little thing that might not be obvious is that you're going to have to subtract 1. So if we, and the reason is that we're going to have to start with the second time step because we know what the answer to the first time step is. It's the initial condition. So we're going to start at the second one. We're not going to count through every element, just all elements minus 1. Okay. So this is going to count through all the elements. And then we say population array iter plus 1. We're indexing in by saying the next one, right, is equal to, I put a little dot, dot, dot ellipses just because my text is so giant. So we can go on to the next line. Okay. Is equal to the, let's pull up our Euler's method right here, right? So this basically is saying that your next time step here is equal to your previous time plus the change times delta t. So the population, so it means the population array, which is the current population, which is the current iteration, plus now we are into the dp dt right here. And what is that? Well, that's this equation up here. It's just alpha times the current population. So plus alpha times the current population, which is again population array iter, times delta t dt, semicolon. And the loop. That's it. Okay. Now we're going to plot the results. I'm going to use the plot command. I'm going to plot our time array on the x-axis, on the horizontal axis, and the population array on the vertical axis. I'm going to make a nice black line. Okay. And just because it'd be hard to see over Zoom, I'm going to add another parameter here. You could say, hey, I want the line width here to be, I don't know, 3. That's pretty thick. All right, I'll let you all take a look at that here. This will make this allow you to plot the results. I'm going to be a good boy and label my axes. Good scientist. This is time in some units that I have not defined. And Y label be my population. Once I have that, hopefully it actually runs. There's a new installation of MATLAB. It's going to have all kinds of interesting. There we go. Get that out of your way so you can see a little better the code. If anyone needs to see any, I'll make this smaller so you can all see. But hopefully you can see the exponential curve increase right there, right? Perfect. Exactly as we predicted. Nifty, great, awesome, cool. All right. But that is not a spring-loaded inverted pendulum. Okay? So how do we get there in 45 minutes? Trust me. That's how we do it. Okay. All right. So here's the thing. So hopefully, any questions about this so far? Hopefully I try to keep it reasonably basic here. but happy to backtrack here. So let's go back to, in the meantime, so now let's go to a system that's a little bit more complicated, right? Okay. So first, a couple things that you're going to notice. So notice that the Euler's method has a few properties, okay, that we want to notice here, okay? So we look x of t plus delta t is equal to x of t plus dx of t dt times delta t, right? We have that Euler's method. All right, a few things we want to notice. Number one, it is derived using an equation where there's only one derivative, okay? And many equations, including our pendulum, have multiple derivatives, okay? So what we would call that is, we'd call that a first order differential equation, okay? First order means only one derivative. Okay, so that's, it applied to, it worked really well for this population model, but how it's going to work with things with multiple derivatives. So I'll scroll back up to my pendulum right here. That's a second derivative right there with respect to theta, right? So how are we going to have to learn how to deal with that? Okay. Number two, it's exhausting to write dx of t dt or d theta of t dt over and over again. So those of us who work in dynamical systems have a very simple way of writing it. We say that dx of t dt, we write it as x dot of t. Saves us carpal tunnel. Okay? That's a common notation, that for every time derivative, you put a dot. So for that equation up above, we would have written theta double dot of t. All right? It's cool. So naturally, you're going to think of, if it's a position variable that you're taking derivative of, a first derivative is going to be your velocity. Your second derivative is going to be your acceleration. I'm going to start asking for more derivatives for people ready to unmute themselves. Anyone know what the third derivative is typically called of position? There's multiple names, but this is a fun factoid called yeah, thanks, Jordan. X triple dot, if it's position, that's called jerk. Some people call it jounce. Yeah, not calling me names, Jordan. I appreciate that. Thank you. Thank you. Anyone know what x quadruple dot is?
Snap.
Yeah, snap. Thank you. X 1, 2, 3, 4, 5. Crackle. And X 1, 2, 3, 4, 5, 6 is pop. And I'm not making that up. I actually tried to find the oldest, yeah, snap, crackle, pop. Tried to find who decided this. Who made this name? I managed to trace it back to at least Usenet forums in the early 90s. People were talking about what they should call them. That's as far back as I've gone, as to who decide, what physicists decided to call them snap, crackle, pop. Anyway, we won't go probably that far to jerk, snap, crackle, pop. But anyway, fun little aside. All right. But the point is, we're going to have to deal with higher order derivatives. All right. Okay. Another thing that you'll notice that there's only a derivative with respect to time, right? That there's no derivative with respect to space. There's no derivative with respect to any other variable, right? And that means it's going to be what we call an ordinary. First ordinary differential equation. Sorry, I can't read that. Ordinary differential equation, okay? So we're dealing with ordinary differential equations, diffEQs, otherwise called ODEs. And we are dealing with first order ODEs. So how do we make Euler's method work when it only works for first order ODEs? There are ways to make it work other ways, but here's a way, okay? The trick is that if you have any higher order ODE with more derivatives, there's always a way to turn it into multiple first order derivatives, differential equations. There's always a way, okay? And it's a pretty simple formula to do it, all right? So let's start motivating our spring-loaded inverted pendulum, and we'll show you how from this example. Okay, the spring-loaded inverted pendulum, otherwise known as the slip model, always an interesting term because it does not slip by definition. Its foot sticks on the ground and it does not move, but it's called the slip. All right, and we're just going to start with a 1D version, meaning it's just going to hop up and down. So we've got a mass, we got a spring, and we're just going to start on the ground. We're not even going to leave the ground yet. So we're just going to have some vertical position, call it Z of t. In legged locomotion, a lot of times up is Z because Y is that way and X is that way, right? Okay. So, all right. So what we can get the equations of motion for our dynamical system, and it's going to basically be our F equals ma, force equal to mass times acceleration, where in our case, our acceleration is going to be Z double dot of t. Okay. And we're going to sum all of our forces. And the only forces we're going to have are going to be gravity and this spring force, okay? And we're going to have some rest length of this spring 0. You need a rest length for your spring, okay? So we're going to, here we're going to derive the equations of motion ourselves. It's not very hard. There are toolboxes, symbolic toolboxes that will do this for you if you have a complicated system. Okay, but here, this just to make it for transparency, we're just going to derive it really quickly. And so we're going to sum all the forces, the free body diagram. Down, we've got mg for gravity. And pushing up, we have some spring constant k times the deflection of the spring. And it's going to be L0 minus the height z of t. Okay. So that means when the rest length is longer than the actual length, that means it's going to want to push it up. And up is the positive direction for z. So when L0 is longer than z of t, positive. Okay. So we sum all of our forces. So is equal to the mass times the acceleration z dot double dot of t is equal to minus mg plus k L0 minus z of t. Okay. There's our equation of motion right there. Boom, 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 boom. Put that to the side. Okay. So how do we simulate that using Euler's method? Right? Because you can see we have a second derivative. Right? So we got to turn this into, we're going to convert this to a system of first order ODEs. Now, how do we do that? Well, what we do is we say, hey, you know what? Instead of just caring about one variable that we're taking two derivatives of, let's create two variables that we take one derivative of. Then we have two first order differential equations. So we would say, hey, let's create, so we create a set of variables that represent the higher order system using only first order ODEs. Okay? So, rule of thumb, if it's a second order system, you need two of these variables, and they are called state variables. Okay. And for mechanical systems, which are typically second order because of F equals ma, or there are multiple second order systems, right? You will need you say, hey, I'm going to have state variables. We'll call them y. And it's a list of them, a vector of them. And we'll say, hey, it's going to be z of t, which is the position, and z dot of t, which we all know is the velocity. Okay? These are our state variables. We put them in a list. Those of you who have ever seen that before, it's a vector. Okay? So so we often call that the state vector. And because it's a vector, you all taken calculus, you all know a vector is a thing that points in a direction. And people are like, oh, mathematicians are like, hey, it's a vector that points in a direction. That means that any position and velocity together means a different vector and points to a different point in space. So let's call it a space. Let's call it state space. And so you'll see these called state space models. Okay? Right? But to understand from a survivalist perspective, it's just a way of turning your higher order differential equation into multiple first order differential equations. And once you have these variables, you can now say, oh, I have this position, I have this velocity. That's all I need to know to simulate my system, right? So another way to look at this is that the state vector here, this list, needs to contain all the variables you need and no more to simulate the system. For instance, if I am going to simulate the trajectory of this marker, right? If I want to know where it goes over time, I need to know where it started, right? And if I don't know the speed at which it starts, I don't know where it's going to end up either. So those are two things I need to know for the position of this marker back and forth, okay? So that's another way to think of the state vector, okay? So how do we use the state vector? Well, what we can do is we can say, hey, this state vector, let's take the time derivative of it, and it changes over time. And that means that we take the time derivative of everything inside the state vector. So z of t becomes z dot of t, and z dot of t becomes z double dot of t. Make sense? We just took the time derivative of this, which gave us that, which means we take the time derivative of this, which gave us that, and then this, which gave us that, right? That's it, right? Okay? Then we can rewrite this in terms of things that we know. What are the things that we know about our system? We'd have to know where it starts in position and where it starts in velocity. So we know what the velocity is. So we just say that z dot of t is equal to z dot of t. So here's a good way. So we know this. We have to know this to simulate. Good. So at any given point in time, the time derivative of position is velocity, which we know. Okay. Now how about this? Z double dot of t, our acceleration. That is not one of our state variables. We do not know it as a stored variable. But can we get it from somewhere? We absolutely can. Whoop, oh, there it is. Right there. And it's written in terms of this, which is stuff we know. So we can just take this equation, solve it for z of t, z double dot of t, and we have written, and I'm just going to solve it just in my head, so I'm sure I'll make zero mistakes. I'm going to solve it by dividing both sides by m, plus k over m L0, plus k over m L0 minus z of t. That's it. Now, this notation may or may not look familiar to you, but really all it's saying is that, hey, we can define the time derivative of position as being equal to the velocity, z of t. That's one equation. And for our second equation, z double dot of t, the time derivative of velocity, is equal to minus g plus k over m L0 minus z of t. Right? That's it. Those are two first-order differential equations. Okay? So that means we can use Euler's method. We just have to do it twice in a loop. Okay? Every loop we do two Euler approximations, right? We would say, in fact, if it helps, you could call it position. Okay, yeah, anyway. So I'll show you what I mean. Let's make we can actually probably do not pass go directly to simulation. So let's pull up MATLAB. Okay. So we're now going to do just a 1D pendulum, 1D spring-loaded inverted pendulum, 1D slip 1D. So let's make a new file, completely new file. I'm going to call it slip1d.m. I'm going to save it. .m, again, written by me and all my friends. That's you. 2025, 08, 21 of the Common Era. This is going to be a simulation of a one-dimensional spring-loaded inverted pendulum. And it's not going to leave the ground. So it's going to stay on the ground. It stays on the ground. Okay? We'll talk about how to get it off the ground in a minute. Okay? All right. So now we're going to, what's the first thing I like to do in MATLAB? Clear everything. This clears the screen, this clears all the variables, and this closes all the plots, okay? And now we need to define our parameters. I'm going to do our simulation parameters first. Then I'm going to do the parameters of the physical model. So we have to define delta t, just like we did before. Let's say 0.01, small time step. It's often called a time step. And if you ever look in the literature, you will also often see this written as the letter H. Okay? See that it's written as the letter H if you're looking in the literature. Okay? You have your time final. Let's simulate this for 10 seconds. Okay? That's the final time. We'll do all these in seconds. Now I understand what the units are because I don't know rodent units of time. All right, time there. That's the simulation parameters. We are now going to get our physical model parameters. And what are our physical model parameters? So let's look at our model here. I see G as gravity. So let's do 9.8 meters per second squared. I'm going to make my initial length be 1 meter. Just to make my life easy. And your spring constant K, I think it's about, I'm feeling 30. Are you feeling 30? I'm feeling 30 newtons per meter. I'm feeling 30. I reserve the right to change my mind. It's my prerogative. Okay. All right. Got physical model parameters. That's great. Now we need our initial conditions. All right. And we need to know the initial conditions of every state variable, of which there are 2. Okay. Right there. For our position and our velocity. Right? So let's call it Z0 is the initial position. We'll start it at let's start it right at rest, like 1 meter at rest. So 1 meter. Okay. And let's also start it with an initial velocity at 0. We kind of just release it at 0 velocity, you know. So dz0 we'll call it. So this is our initial height in meters. This is going to be our initial velocity in meters per second. We're just going to start it on the ground, just release it, see what it does. Okay? Now, we start to talk about pre-allocating our vectors, right? So let's call it our time array. Let's do the same thing as before. We start at time 0. And we're going to go in increments of dt, and it counts up in increments of dt all the way up to t final. Okay? We're also going to do a position array. I'll call it a Z array. Is going to be the same. It's going to be, we'll start it off with some zeros of the same size as our time array. Okay. This just creates a bunch of zeros, the same size of the time array. And then I'm just copying it. I'm being really whimsical and fast. And so I just DZ array. And if you're curious how I'm whippy-doing around the screen, everyone has their own tricks. What I do is I use shift and I hit home and I hit end to go back to the right. And, you know, that's what I do. So I'm just using home and shift and end to go around in case you're curious. Everyone has their own approaches. Okay. So we pre-allocated vectors. Now that we do the simulation loop. Okay, this is going to be the Euler simulation loop, and so we'll use another for loop. We'll do the same thing as before. We'll count up this iterating variable I like to call iter from 1 to the number of elements, NUMEL, and number of elements in our time array. And again, we're going to subtract 1 because we already know what the first one is. In fact, I forgot to define what the first one is. So we're going to say Z array, the very first value, is going to be equal to Z0. Okay. And we're going to say the very first velocity, DZ array, first one, is going to be equal to DZ0. Done, right? Okay. Simulation loop. All right, so we have for iter 1 colon numl array. Great. Now we need to do our Euler's method approximation. All right, so we can say, according to our math here, that this means that of our state variables, we would say that Z of t plus our delta t is equal to our current Z of t plus our time derivative, which is going to be Z of t at the current time, times delta t. Hope we can see that well enough. I'll make it a little bit bigger. Boom. Right? So that means we would say that the next element of the Z array, iter plus 1, the next one, is equal to Z array, the current one, which is iter, plus dot, 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 Z of t at the current time, which guess what? We know what that is. It's DZ array at the current time. So we'd say DZ array, that's our velocity, at the current time, which is iter, times delta t. That's it. Those terms right there. Now we just got to do the same thing again for the DZ array. All right, where Z dot t plus delta t is equal to the current Z dot. I'll make this a little bigger here so you can see. Current Z dot of t plus the time derivative of that, which is Z double dot of t times delta t. That's Euler's method. You know, the next step is equal to the previous step plus the change times delta t. Boom, right? So that's what that is. So now we'll do DZ array iter plus 1 is equal to the previous DZ array iter plus dot 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 Z double dot, which we determined is this equation right here. Now I could write this all into the line, or I could not do that. I'm going to just write up above here, I'm going to define ddz on a different line to make my life a little easier. It's going to be equal to minus g plus k divided by m. Did I define m? I didn't define my mass, friends. I didn't define my mass. Oh boy, I'll get right back to it. Did I define L, and it times L0 minus z of t. See that? It's all right there. Minus z of t. So whatever our current position is, so it's Z array iter. This is just a cleaner way we define the acceleration on different lines, so it's all not on one line. That's all I'm doing. I'm also noticing I did not define, did I define L0 and K? I defined L0, K, and I never defined M. So scrolling up, M is 1 kilogram. Boom. Great. Okay. M is now defined as 1. We have these double dot. Now we go back down to Euler's method right here. So now we're going to add our second derivative, which is d dz times delta t. And that's the loop. Some people write the right end loop. Sure. Okay. All right, now we just need to do some plotting. Let's do some plotting. We're going to plot the height over time. Okay, so that's going to plot our time array. And I'm going to plot our z array. And I'm going to make it a black line. I'm going to do my line width as 3. All right. Label my axes. It's going to be time in seconds. And my y label is going to be our height in meters. All right. We did that right, and I run it. That should create a nice little plot for us. Look at that. It's springing, to use a technical term. But the physicists among you, or the physics inclined among you, might notice a little issue with the simulation. Does anyone want to point out what might not be quite accurate about my model here? What about the simulation? This is a energetically conservative system. And yet, because it's just, if I go back to my equations here, my system, it's just a spring, no losses, no impacts. It shouldn't be gaining or losing energy. And yet, looking at my plot here, it's gaining energy. It's oscillating. It's going woo, 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 right? Why? What, do we screw up? Well, one thing you got to remember is that Euler's method is an approximate method, right? It's an approximation. Assuming that you've picked a small enough, the spring has no max length. That's another thing. It will launch into the air without a max length. That's true. That's also true, Autumn. We will get to that in 15 minutes. Watch. But even more importantly, that dt that I chose, I kind of hand waved that I chose, 0.01, might not be small enough. Let's make it 0.001 and rerun it. Much better, right? Not gaining as much energy. That's because, if you recall, from Euler's method way the heck back here, here's Euler's method. Look at that approximation, right? Whoa, there it is. It assumes it's small enough, right? And so I'm assuming that some of you are asking yourselves, well, how do you know if it's small enough? Great question. And there is a whole numerical science to determining that. But there are tools inside of MATLAB and most programming languages that will choose it for you. Or even more importantly, it will determine when in the simulation it needs to be smaller than others. Okay? Like if this system is not accelerating very much, having a long time step's totally fine. Just like if you were in your car, if you knew you were going exactly 60 kilometers an hour, you're going exactly that speed, you could say, oh, that means in an hour from now, I'll know I'll be 60 kilometers away, just because I know that super precisely. But if you're speeding up and slowing down a lot, you would have to use smaller and smaller time steps to make that calculation, right? So in MATLAB, there's actually a function for it. It's called ODE45, and there are many versions of it. Let me see if I can get this bigger here. I don't know if I can make that bigger in the moment, but you can say help ODE45, and it is a method of simulating ordinary differential equations, ODEs, if you give it the right information. Well, what information is that? Oh, it integrates, and if you can read that, a system of differential equations. Y prime is equal to f of ty. A system of first order differential equations. Oh my goodness, isn't that exactly what we were doing? Yes, it was, right? The way we've been defining these systems, look, a couple of first order differential equations right there, right? And ODE45, and it's just one of many methods that they have, allows you to then to simulate more accurately. Well, let's use it really quickly, okay? It's just so you have an example, because it's such an important tool, okay? But the idea is if you can define your state vector, remember we talked about it, y. Oh my goodness, it's almost like I didn't make all this up. It's like it's a real thing, right? You know, it has a bunch of state variables in a list. We'll call them, they can be anything. They could be, you know, y1, y2, whatever, is equal to some function of time and state. And that's literally what we did for our spring-loaded inverted pendulum here, right? We rewrote and y dot of t. There we go, y dots, right? We wrote the derivative of our state as being dependent on just states and also time, okay? So if we wanted to use ODE45, how do you use that? Let's pull it up. Let's have ODE45 do the same thing. What do you need? So ODE45 says it needs a couple of things. It needs an ODE function, which is those equations that I showed you. We're going to put them in a new function file, okay? A time span and an initial condition, okay? So what I'm going to do really quick is I'm going to create a new file. It's going to be a function file. It's going to be function, and it needs to return one thing. It's called y prime, or dy is equal to ODE, and it takes in the current time and the current state y. So for instance, for our, we'll call it ODE fun, because it's enjoyable. Okay? Inside the function, we would have to define our mass, our gravity. There are ways to define it outside and pass it in. We can talk about that offline if we want, just make sure we have time here. And is that all we need? L0G, yeah, I think that's it for inside the loop. I think that's it.
You don't need K?
K. Okay, thank you, Monica. Thank you, much appreciated. Okay, I'm being sloppy and defining this really quickly without comments. All right, but what you need to do is send back the derivatives of your state depending upon the current state. So thankfully, we can define our first state here. We're going to say that z of t, the derivative of our first state, z of t, okay? Call it dz. Oh, sorry. So our first state is going to be the first element of y. So it's y of y1, okay? Because it's the first one there. It's defined it there. And dz is equal to y2. This is our position. We call that the first state in our little list here. And here we got our second state, velocity. Second state. Okay. We got the states in from y. And now our job is to send back dy, the derivative of each of these states. Okay. So dy, we got to send back in a vector. First, the derivative of z, which we know is dz. Well, guess what? We now know dz, right? Done. This is the derivative with respect to time of each state. And the derivative of our second state, z dot, which is going to be z double dot, otherwise known as minus g plus k over m times L0 minus z. Done. And so what ODE45 does, and there's other, what it does is it needs to be given this function, And that's how it knows what your dynamical system is, okay, for it to simulate, okay, and for it to solve. So really quickly, I'm going to create a new function file, a new script file. I'm going to call it slip 1D ODE45.m to show you how easy it is to use. Slip 1D ODE45.m. Make this really fast. CLC clear, close all. Not even commenting well. Shame on me. And then we're going to use ODE45. All we need to define for it is the ODE function. So it says it's going to give us a time vector t, so a time array, and it's going to give us a state array. And ODE45 requires that we give it an ODE function. And the way that we tell it it's a function, we say at ODE fun. Then you have to give it a time span. Put that in a little vector. Actually, I'll define it up above so you can see the time span. Where do you want it to start? Where do you want it to end? 0 and 10. Okay? And also we need to know our initial conditions. So our initial position, which is our first variable, is 1. Our initial velocity is 0. So we give it the time span. And we give it y0. And ODE45 will simulate our system. It'll choose all of its own little delta t's at different points of time that it seems that t's are appropriate, and the states at each of those points in time. Okay, so I'm going to run it. I'm going to show you what's in these timer. Oh, what did I screw up? What did I not define here? ODE fun. dy, all in logical energy possible. Oh, I forgot the multiplication there. See that? Actually, I have this fancy device. Work. Anyway, you can see that multiplication that I missed. Gotta save it. Gotta rerun the code, make sure it works. And you can see that the time array, if I just hit time array, enter, you can just see it's a bunch of points in time that it chose how fast they should move and not. You see that the increments are not consistent. It's choosing when to have small time steps and when to have big time steps. And if you look at the state array, what is it? It's 2 columns. It's going to be the same number of rows as time steps. So this entire first column is our position, and the entire second column is our velocity. Okay? So if we want to plot our position over time, we plot our time array and just the first column of our state array. And in MATLAB, if you want the whole column, you say, hey, I want all the rows, which would be colon, comma 1, which is the first column. Okay? Then I'm going to make it there, and I'm going to make the line width 3. Should be able to run that. And there you go. It chose the time step so that way the oscillation doesn't get bigger and bigger and bigger and add more energy, right? It was smart about it. Now, how does it do that? The way it does it is it actually uses a higher order integration method called Runge-Kutta. And there are many versions of it. There's like a 4th order and a 5th order. And 5th order is going to be better than 4th order, right? And you can keep adding more and more orders that are more and more precise. And what it does is it says, I'm going to try doing a 4th order step and a 5th order step and see how different they are. And based on how different they are, that tells me how much smaller I need to make my time step. That's why it's called ODE 4-5. It uses those 4th order and 5th order methods. At least that's the simple way I like to explain it to people. So it's actually not too complicated to code up. So that's how you can have it choose the time step for you, right? But one thing we haven't done is limited the we have not limited the length of the spring. I forget who mentioned that. We're going to make this jump. I promise we'll make it jump, and we have 4 minutes. I think we can do it. I think we can, friends. All right? And this is where it gets a little bit tricky. I'll give you the high-level version. So because what we have done is we have defined our dynamics as this one differential equation, right? That one differential equation defines our dynamics. But our dynamics are different when our feet are on the ground versus off the ground. We have to switch between whether or not we have a leg on the ground, and whether we have a leg on the ground, therefore have a spring force, versus when we don't, okay? And when you have a switch in those dynamics, it goes from being called what we would call a continuous dynamical system to what we would call a hybrid dynamical system. Legged locomotion is commonly understood to be a hybrid dynamical system. If you talk to hardcore mathematicians about it, they would say technically a hybrid dynamical system is when your state jumps instantaneously at some point and then smoothly moves again. Hey, we talked about state. We know what state is. It's the state variables, right? That's what they're talking about. And colloquially, I just like to say it's when the dynamics switch. Well, here we have a pretty easy way of doing this. So the only difference for our little model is that when it's in the air, it's only under the force of gravity, not the spring. So what I'm going to do is have a little if statement that says, if I'm past the spring length, okay, I'm going to make the spring force 0. That's all I'm going to do. Super easy version of this. There are smarter versions, which I will hint at, because I think we can actually do this in 90 seconds. Okay. So here, I'm back in my slip 1D code, and I have this DDZ command. So what I'm going to do is I'm going to say F, the force in the spring, is going to be equal to all of this. Okay, I'm going to cut this out, cut it there, and say, and I'll get rid of the divide by M. The force in the spring is going to be that, F spring divided by M. You can check the math, that math should work, right? That should be the exact same result if I run it. Where did I screw up? Oh, extra parenthesis there. If I run it, I should get the same result I got before. Sure enough, I did. Okay? So what I'm going to say is that if Z array iter, the current height iter, is greater than L0, that means it's off the ground. That means the force in the spring is 0. Otherwise, else, otherwise, the force is the force in the spring. This switches to flight, switches to stance. We know the flight and stance from, right? So now if we run this, nothing is really any different because it doesn't really start off the ground. But if we change the initial condition from being 1 to being, I don't know, 1.5, and we rerun it, there we go. It hops, hits the ground, hops, hops, hops. It might not look a lot different, but the shape of when it's in the air versus on the ground is different. Okay? It's hopping. All right? So very simply, we change the dynamics into a hybrid dynamical system with an if statement. This is a little bit sloppy because the time step for when it hits the ground, the time step might miss the exact moment where it hits the ground. So it might accrue a little bit of error. This is one way to go. But actually, ODE 4.5 has a beautiful way of detecting when an event happens like hitting the ground. It's called event detection. And I can stick around for a few minutes afterwards to show you how that works. But otherwise, that's how you simulate a system in a nutshell. I mean, how do you get that to running forward? Well, all that changes is that you have your equations get more complicated, okay? But the same procedure applies. You take every position and velocity, you put it into your state vector, and you arrange it into that form, except now you would have a forward position and a backward position. You would probably, if you had a spring-loaded inverted pendulum that's moving forward like that, where that's x and that's z, you would now have a state vector that has x, x dot, z, and z dot in it. And then in the code, you would have 4 of these lines instead of 2. There are nicer ways to write it. I cover it in my optimal control class if you're curious, but thank you for taking me out 90 minutes. I'll pause there. Thank you so much.
That was great. Thank you.
Thank you. Any questions or any thoughts before I go? Let me show.
Would you mind explaining why you chose the current value of z to be greater than L0 as the if statement that switches to flight?
Oh, great question. So so why did I choose this condition to be greater than or equal to flight? So I forget, Autumn mentioned like, hey, we don't have a maximum spring length, I believe, in the chat before, if my memory serves. So if I go to my diagram, okay, the rest length of the spring, when you are compressing that spring past the rest length, right? That means the spring's in compression, right? And so that means the spring is pushing against the ground is pushing back against the spring, which allows you to spring up. Now, when the spring lengthens, so when you're past the rest length, when your height's past the rest length, right at that instant, your force is 0, right? You're at the rest length of the spring. Then you go further up, okay? Then if you're still on the ground, that ground's got to tug you back down, right? But that's not how the ground works. The ground does not suck you to the ground with a suction cup. The ground only pushes force one way, and that's up, right? We call that a unilateral contact, just so we sound fancy. There's just contact force in only one way. It's unilateral, right? Which means that it can't suck you back down. That means you're off into the air. Therefore, you're in flight. So that's why when we pass the rest length, because it can't tug us back down, we have to enter in flight.
Okay, yeah, that makes sense. Thank you.
Oh, yeah, it was you who asked. Yes, exactly.
Yeah.
Yeah. Any other questions? All right. Just pop in at any point. I will say I will not be offended if you have to go. But I'll just point out the thing that with the ODE event detection, it's very similar to how the ODE 4.5 works, where you create, instead of a function that defines your dynamics, this is your ODE function that we defined, you create an ODE events function. And it takes in the current time, whatever the current time is, or whatever the current state is, and you tell it how close it is to hitting the event. And so that's how you can have it detect if it hits the ground or not. And what you will do typically is you say, when it hits the event, stop the simulation. And then what you do is you rerun ODE 4.5, you change the dynamics, you change the state, you do all the things that you want to do, like what we did on this math right here. Sorry, like what we did, which is what we turned off, where we turned off the force and on the spring, and then you restart it again. So you keep turning on and off the simulation. That's how it typically works. All right. I really thank you all for following along and your attention. I had a great time, and I enjoyed a lot of the workshops this summer. So thank you all to the prior workshop attendees. Definitely open for next year, simulating something more appropriate to muscle modeling and things like that. I was trying to see if I could fit in a hill type today, but I think we got plenty in today.
Yeah, that was a lot in the time you had. If there are people who are interested in learning more, are your other lectures available online?
I'm gonna put them up on the Slack right after this. I have a YouTube playlist of my last time I taught applied optimal control. Now, don't be, if you're like, I don't know what control is or how to do control, don't be afraid. A lot of it is designed just like this was, assuming that you've never done a simulation before. So there's a little, so I do tutorials in MATLAB. It's all in MATLAB on how to do simulation and then optimal control. So I'll post that YouTube playlist for the entire 2025 semester of courses.
Great. That would be a good resource. Thank you.
All right. Thank you so much. I appreciate everyone.